Alright, we'll have two other lectures dealing with probability after this one. This one is on basic probability, fundamentals of probability, and we're going to talk about theoretical probability as well as empirical or experimental probability. This might be one of the easiest things you've learned in this class. You're probably familiar with some of the things I'm talking about, that I'll be talking about. Okay, when we talk about probability, keep these things in mind. Probabilities are assigned from values from 0 to 1, or another way to think of it is from 0% to 100%. And the closer the probability of a given event is to 1, the more likely it is that the event will occur. In other words, if you were going to roll a die and I said, what's the probability of rolling a number greater than 1? Well, there's 5 numbers greater than 1 on a die, so it'd be 5 out of 6. So we'd be way up here at about 86 or 87%, which is really likely to happen. It's not necessarily going to be certain that it happens, but it would be likely that it would happen. And then naturally, the closer the probability of a given event is 0, the less likely that the event will occur. What if I said you're going to roll a die, what's the probability of rolling a 7? Well, the probability of that's 0, so that's impossible, or 0%. So it's going to range anywhere from 0 to 1, or 0 to 100%. Probability does. Okay. Now, theoretical probability, there's a few terms we should talk about. An experiment is any occurrence for which the outcome is uncertain. That might be spinning a spinner, rolling a die, flipping a coin, shooting a free throw, bowling a strike. Those are all examples of experiments. A sample space is a set of all the possible outcomes of an experiment, and it's usually denoted by S for sample space. What that is, let's say for flipping a coin, there's only two parts of the sample space, either heads or tails. When you roll a die, there's 6 elements of the sample space. 1, 2, 3, 4, 5, 6. Okay, that's what a sample space is. It's a set of all the possible outcomes. Event, denoted by E, is any subset of a sample space. So an event might be, let's say the sample space is shooting a free throw, so the sample space is make it or miss it. An event would be one of those two things, such as make the free throw. Rolling a dice, the event might be rolling a 2, whereas the sample space is 1, 2, 3, 4, 5, 6. And then another thing to keep in mind is the sum of theoretical probabilities of all possible outcomes is always 1. If you think about it, what's the probability of if you flip a coin once, what's the probability of flipping a heads? Well, that's 1/2. Flipping a tails is also 1/2. Well, when you add those two together, 1/2 plus 1/2 is 1. The sum of the probabilities will always be 1 on an experiment. Okay, just one second. All right, let's go to the next slide. Had a phone call there, so little interruption. There we go. Computing theoretical probability. I'm going to show you 2 ways, and you decide which one you like best. The official way the book lists it is if an event E has n of E equally likely outcomes, and the sample space S has n of S equally likely outcomes, the theoretical probability of event E denoted by P of E is, and here's what they tell you, that P of E, which means the probability of the event happening, is n of E over n of S. And n of E is the number of outcomes in event E, and n of S is the total number of possible outcomes. Now, if you like that definition, use that one. I like this one better. The probability of something happening is simply the number of desired outcomes over the number of total outcomes. So if I ask you what's the probability of rolling an even number on a die, well, the even numbers on a dice are 2, 4, and 6. So there are 3 desired outcomes and there's 6 total outcomes, so the answer to that would be 3 out of 6, or 1/2, or 50%. So use whichever definition you like. I'm probably going to use this bottom one here as we go through these next example problems. Okay. Here's a picture of a die over here, like when you play Monopoly, you use one of these. Actually, you use 2 when you play Monopoly. But we're just going to roll one die once. Find the probability of rolling a number greater than 2. So we're looking for the probability of a number greater than 2. Well, the probability of a number greater than 2 is a fraction. And on the bottom of the fraction are the total number of outcomes, which is 6, because there's 6 numbers on a die. The sample space is 1, 2, 3, 4, 5, and 6. Okay, how many numbers are greater than 2 on a die? Well, there's 3, 4, 5, and 6, which is there's 4 numbers greater than 2. So the probability of rolling a number greater than 2 is 4 out of 6, or simplified as 2/3, or as a decimal, because on MyMathLab sometimes they ask for it as a decimal, would be 0.66666, etc., repeating, or as a percent. We move the decimal over twice and we get approximately equal to 66.7% or 66.6% repeating. Alright, now, don't know why my 7 keeps disappearing there. Okay, what's the probability of rolling a dice once and rolling a 7? Well, we talked about this earlier. The probability of rolling a 7 is 0 out of 6, or just plain old 0, or 0%. It's not going to happen. Alright, now I want to warn you ahead of time, if you're not a card player and if you're not used to decks of cards, you want to get familiar with them because there'll be problems on MyMathLab dealing with decks of cards, and on my Module 5 exam there'll be problems dealing with decks of cards. So keep in mind, on a deck of cards there's clubs, diamonds, spades, and hearts, and there's 13 cards of each suit. Ace, deuce, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. The jack, queen, and king are called face cards because it's kind of obvious, they all have a face on them. Jacks, queens, and kings are face cards. Now, so if I said what's the sample space when you're dealing with a standard deck of cards, that's a diagram of the sample space right there. There's 52 cards, so the sample space consists of 52 cards. Now, let's say you were dealt one card from a standard 52 card deck. Find the probability of being dealt a king. Well, as you can see, there's a king of clubs, a king of diamonds, a king of spades, and a king of hearts, so there's only 4 kings. So the desirable number of desired outcomes is 4, and the total possible outcomes is 52. So your probability of drawing a king or of being dealt a king is 4 out of 52, or that reduces to 1/13 or simplifies to 1/13. What's the probability of being dealt a heart? Probability of being dealt a heart is 13 out of 52 because there are 13 hearts, which is our desired outcome, and there's 52 total, and that reduces to 1/4. That diagram there kind of shows you why it reduces to 1/4 or simplifies to 1/4. Now that we kind of have the basics down, let's see if you guys can figure this out. You're dealt one card from a standard deck of 52 card deck. Find the probability of being dealt a face card. So we want to know the probability of a face card. Well, if you forgot, there's a jack, queen, king of hearts, diamonds, spades, and clubs. There's 12 face cards. So the desired outcomes is 12. The total outcomes is 52. So there's your answer. The probability of being dealt a face card is 12 out of 52. That would reduce to 3 out of 13. If we divided both the numerator and the denominator by 4, we'd get 3 out of 13. Now, if we wanted that as a decimal, remember, all you do is change a fraction to a decimal, because like I said, my MathLab might ask for a decimal. You'd take 3 and divide it by 13, and we'd get approximately 0.2307. 0.2307. And if we wanted it a percent, it'd be approximately 23.07%. So be used to giving the probability as a fraction, a simplified fraction, a decimal, and a percent. Okay, what's the probability of being dealt a red card? Well, the probability of being dealt a red card is simply 26 out of 52 because half of the cards in a deck are red. which reduces to 1/2 for obvious reasons. Okay, how about if we spun this spinner? We're going to spin it once. What's the probability of spinning a green? Well, notice there are 8 sectors on this spinner, and only one of them is green. So the desired outcome is 1, the total outcomes is 8, so the answer is 1/8. How about a star? There's 1, 2, 3, 4 stars, so 4 out of 8, or 1/2. Or like I said, we could change these to percent, would be the probability of spinning a star. How about a red star? There's only one red star, so that'd be 1 out of 8. How about a diamond? Looks like there's 3 diamonds, 3 out of 8. Green heart. We're not going to find any green hearts there, so the probability of that is 0%. You could say 0 out of 8 if you wanted, or you could just say 0, or you could say 0%. Any of those are okay answers. Now, how about the probability of spinning a heart or a star? Well, here's a heart, and then we have 1, 2, 3, 4 stars, so there's a total of 5 desired outcomes, so 5 out of 8 would be the correct answer for that one. And then how about red or blue? Well, it's almost easier to look. Right here there's only one green and everything else is red or blue, so 7 out of 8 would be the probability of spinning a red or a blue. Okay, the only other thing we want to talk about is experimental probability. It's also called empirical probability, and these apply to situations where we have observed something in the past. So maybe you've observed a person bowling strikes, or you've observed a coin getting flipped 100 times. So we have something to go by already from a previous experiment. Here's an example of empirical probability. Here are the statistics of a Gillette College point guard's free throws in the last 4 games. Versus Sheridan College, she was 5 out of 6. Versus Eastern Wyoming College, 3 out of 6. Western Wyoming, 2 out of 2. And against Bighorn College, she made 1 out of 3 free throws. Now she's fouled with 0.1 seconds left in the game, in a tie game, and gets to shoot 1 free throw. And it's 1 free throw because it's a 1-and-1. If she makes it, they win. If she misses, it goes into overtime. What's the probability as a percent that Gillette College will win the game? I should have said will win the game in regulation without overtime. Well, let's go back and look at what's happened in the past. If we total this up, she's made 11 out of 12, 14, 17. 11 out of 17, and we said as a percent, so we're going to go down to the calculator here. We'll take 11 divided by 17, and that gives us 64.7%. 0.647 is 64.7%. So that's an example of empirical or experimental probability. I think I have one more example right here. Let's say 242 people living in an apartment complex in Gillette were surveyed and the results are tallied above. If one person is randomly selected from the population described above, find the probability that the person is female. Well, if you just look at the table there, there's 242 total people and there are 124 females. So the probability of randomly choosing a person and having it being a female is 124 out of 242, which is about 0.51%. Okay, looking at that same, how about if we randomly selected someone from that apartment complex? Find the probability that the person is, let's go down to this one, male and divorced. Okay, well, there's male and there's divorced, so it'd be 10 out of 242. 10 out of 242, and then that could simplify to 5 out of 121, and we could change it to a decimal if we wanted. One last slide. I want to make sure you guys understand this. Sometimes it's helpful to list the sample space to help you solve the probability problems. For instance, if a fair coin is tossed 2 times, find the probability of getting 2 heads. That might be tough to do unless you did this first. List all the probable outcomes, which is heads, 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 tails, heads, heads, tails, or tails, tails. That's what could happen if you flip a coin twice. It could be heads, heads, tails, heads, heads, tails, or tails, tails. So what's the probability of getting 2 heads? Well, you can see the only way to get 2 heads is right here, which is 1 out of 4. And we could answer all those other questions using that sample space also. Okay, thanks for watching this lecture. Goodbye.